So suppose G is a group and H is a subgroup of G, and we look at all the automorphisms of G from itself to itself. So G to itself. So we take another copy of G maybe. What is an automorphism? And this I said in the previous discussion, that automorphism is a special function, a special map from G to G, which maintains the structure of G. So basically phi of A star B is equal to phi of A star phi of B. So we talked about this in the previous video. You can look into it one more time. So what is aught G? Aught G is the collection of all automorphisms of the group G. So all possible functions of the group G, and there could be infinitely many of them depending on the group G. So all functions in the group G from G to itself which have this property phi of A star B equals to phi of A star phi of B. Of course, we also want the additional property of bijection. So an automorphism needs to be a bijection and needs to have this property. Okay, so we look into a group and we look into a subgroup, a very special one, very special subgroup of G, which has a peculiar property, and that is it is invariant under this automorphism. In fact, it is invariant under any automorphism of the group G. So it's we can draw H here like this, and let's draw the copy of H here like this. So H goes to H under the automorphism, in fact under any automorphism. Of course, the points inside H can move from here and there inside H. That can happen, but as a set, H goes to H. And this is not only happening under a particular automorphism, this is happening under all automorphisms. So H has in some sense a super invariant property. One example of such a subgroup which has this property is the commutator subgroup, and this is a very good example to get your hands on some group theory, some computations in classical group theory. So you can try to show, this is goal, you can try to show commutator subgroup. Of course, we have to know what is that, has this property. In fact, any group which has this property, that it is invariant under all automorphisms, is known as a characteristic subgroup. That is a characteristic subgroup. So one more time, what is a characteristic subgroup? H is a characteristic subgroup if H, phi of H is equal to H for all phi. So for any map in the automorphism group of G. So to do this effectively, we have to of course know what is a commutator subgroup. You can imagine why we are interested in this kind of subgroups which are invariant under every automorphism. It is motivated from a very fundamental idea of mathematics, that if something does not change, it is probably important, and this is called the invariance principle. So if something does not change in a system, then it's probably important to understand the system. This is sometimes called the invariance principle, and this is used in various sections of mathematics, and this is its output in group theory. So commutator subgroup is an example of the characteristic subgroups that we are talking about. So what is a commutator subgroup? So suppose we take any two elements G1 and G2, So G1 and G2 are elements in the group G, and we compute G1 G2 and we compute G2 G1. We ask, are these elements equal? If it is a commutative group, if it's an abelian group, then these two will be equal. If it is not, then they might not be equal. So if they are not equal, then we have G1 G2. We can multiply G1 inverse here, and then we can multiply G2 inverse here. So G1 inverse G1 will become identity, G2 inverse G2 would become identity. So G2 inverse. So question is G1 G2 G1 inverse G2 inverse, is this identity? The answer would be yes. The answer is yes if G is abelian. Abelian means if it's commutative, that is if G1 G2 is equal to G2 G1. But it might not be true if it is not abelian. So it might not be true if G is not abelian. So in that case, this particular element is interesting. This one is interesting. Why? Because of course it tells you how far this group is from being abelian. So we will be talking more about this commutators element and commutator subgroup. So you take, so this element G1 G2 G1 inverse G2 inverse, this is known as G1 G2. It's written in the square bracket like this. You collect all the elements of this form, all these commutator elements, and you also take all products of them, all possible products of them. So G1 G2 times G3 G4, maybe something like this, and their inverses. So you collect all possible combinations of these commutator elements and you get a set C. So this set C is a subset of G. Of course, you're making it with elements of G, so of course it will be a subset of G. But we will be showing that C is a subgroup of G, and not only that, C is characteristic in G. So think about these a little bit, and we will be back in the next video with some more fun in group theory. Thank you.